Will our universe expand forever? Will it slow down its expansion, or will it literally collapse in a big crunch? Is there anything we can do about it? If you're afraid of the heat death of the universe, then this is the video for you. When Einstein developed his general theory of relativity, it provided a way to model how space and time intertwined in a fabric called spacetime would be affected by the presence of matter. This theory essentially gave us the ability to simulate the evolution of the entire universe from a tiny hot point, infinitely dense, to the vast cold expanse that we see around us today. It worked amazingly well. So well, in fact, that it accurately predicted the bending of light around massive objects, which was later confirmed by observations of stars in the vicinity of the Sun. However, when scientists used it to try to model the evolution of the universe as a whole, they ran into an issue. Einstein's equations predicted that the rate of expansion of the universe should either increase or decrease. But observations showed that it was staying constant. This meant one of two things. Either Einstein's theory was wrong, and the rate of expansion of the universe is changing in a way we don't yet understand, or there is some sort of force acting on the fabric of space-time itself, pushing everything away from each other at a constant rate. The latter seemed quite unlikely at first, but over time, this idea has gained traction as observations have shown that not only is the expansion rate constant, but it's actually accelerating. What's driving this acceleration? Enter dark energy. Scientists hypothesized that there must be some sort of energy field permeating all of space, and this dark energy would explain why distant galaxies are moving away from us faster than if gravity was the only force acting upon them. Now, the trouble with that is that while the amount of this dark energy required to match the observations is very small, it still amounts to roughly 70% of the total energy content of the universe. And given that we can't observe nor interact with it, scientists have been left scratching their heads trying to figure out what exactly it is. This lack of understanding has left open the question of whether the accelerated expansion of the universe will continue indefinitely. What will happen to the universe in the far future depends critically on the fate of this dark energy. There are three main possibilities. Let's explore each of them. The first is that the expansion of the universe will continue to accelerate until everything in the observable universe is at an infinite distance from each other. In other words, the universe will expand forever. It may sound boring, but this scenario is consistent with several observations, including the fact that there aren't any signs of slowing down anytime soon and the apparent flatness of space. However, there are a couple of problems with this idea. First, it requires that dark energy exists in a false vacuum state. A false vacuum is a state of lowest energy, like at the bottom of a valley, except it's not truly the lowest energy state possible. If it were true, then it would just sit there forever. But in the case of a false vacuum, something can come along and kick it into a lower energy state, kind of like nudging. A ball at the bottom of a valley over a hill and onto a flat plane where it can just keep rolling forever. In our universe, this could happen if the dark energy suddenly becomes unstuck and rolls down to a lower energy state. But in a broader sense, this is also an example of what physicists mean when they say that the universe has a heat death. At some point, all the stars go out, leaving behind only cold, dead remnants. No more stars means no more sources of light. And since light is what allows us to see, we'd be left in total darkness. Not too exciting. Another problem with the Big Freeze is that it doesn't quite add up mathematically. That S, because the equations describing the behavior of our universe also require that space itself has a curvature. When you lay a sheet of rubber on a table, it appears flat. But if you look at it from an angle, you can see that it's curved. In the same way, space can be curved even if it looks flat. And it turns out that the amount of curvature tells us something about the average density of the universe. If the universe were to expand forever, the average density would approach zero. But observations tell us that the density of the universe is very close to a critical value. This apparent mismatch between observation and theory is known as the cosmological constant problem. To resolve this, scientists have proposed a few solutions. The most popular one is that the dark energy density increases as the universe expands, so that its contribution to the overall matter-energy budget stays roughly constant. Unfortunately, this is just kicking the problem further down the road, because now we have to explain why the dark energy density does that and how it's related to the rate of expansion of the universe. But wait, there's more. Another option is that the expansion of the universe slows down, which is known as the heat death. The heat death occurs when the expansion of the universe, driven by dark energy, is overcome by the attractive force of gravity. Eventually, everything in the universe would literally fall back together into a single infinitely dense point, often referred to as the Big Crunch. On the way in, everything would be heated to unimaginable temperatures before being crushed together into a quark gluon. Plasma similar to the conditions just after the Big Bang. From there, the universe would collapse in on itself, bouncing back into another hot phase of matter known as a quark star, restarting the universe. Some scientists even think that this cycle of expansion and contraction could repeat indefinitely, giving rise to an oscillating heat death. Now, this might sound a little familiar. You see, this idea isn't all that different from our own Big Bang. After all, the Big Bang wasn't an actual explosion, but rather a rapid expansion of space itself. So why can't the Big Crunch be thought of as just a reverse Big Bang? Well, the problem is that there's a missing piece of the puzzle. Scientists have no idea what triggered the Big Bang in the first place, so it seems highly unlikely that they'll be able to figure out how to trigger the Big Crunch in order to avoid the heat death. Luckily, there's another possibility. We don't know whether dark energy is a constant or changes with time, let alone how it behaves under extreme conditions. As such, there's nothing forcing it to have a simple relationship with the rate of expansion. It could change in a way we haven't thought of yet, causing the rate of expansion to slow down without the universe collapsing in on itself. So, which one of these scenarios is the most likely? To be honest, we have no idea. Right now, the only thing we know for sure is that the rate of expansion of the universe is constant. But that could change with time. And who knows, maybe one day we'll find a way to control dark energy ourselves and decide the fate of the universe. Maybe we'll get bored of this heat death scenario and just jumpstart the big crunch. Just kidding. Don't click off yet. As we wrap up this episode, I want to tell you about something that's very important to me personally. That S because I created a free science newsletter a few years ago that now has over 100,000 subscribers. The goal was to create something special, a place where people like you can learn about the latest discoveries and breakthroughs in science and technology in a clear and concise way. I wanted a place where everyone who loves learning about STEM could come together and feel a sense of community. Well, good news, because that dream is now a reality thanks to your support and the support of other readers like you. I'm excited to share this new platform with you, and I hope you find value in it. And even if you don't, you can still help others by sharing it with someone who might. Thanks for watching.